Great. Hi, everyone. My name is Chris Friedt. Oh, my metamates. Thank you. Yeah, I'm Chris Friedt. I'm software engineer, ASIC firmware at Meta. And yeah, this is my talk on supporting native Posix on macOS. So, oh, does the clicker work? I haven't practiced this part yet. Hopefully this works. No? Okay, I'll use the spacebar. Okay, yeah, so about me, I'm a double E with a specialization in RF engineering and antenna design by training, but I've actually just been doing embedded software for years and years and years, about 17 years now. So it's kind of, life is what happens when you're making plans, and yeah. So yeah, I've been doing embedded Linux for a long time. I'm an open source advocate. I started out with, like Gentoo Linux decades ago. But yeah, and I started out as an individual contributor in Zephyr, kind of working for myself, which was an interesting change during the pandemic, but it seems it worked out for the better. And then I started at Meta just over a year ago. So I have some community roles. I organize the Linux Plumbers IoT microconference every year, and this is the 4th year for us. It's happening, this is shameless plug, sorry, this September in Dublin, Ireland. So if you or anyone you know has a talk on IoT, pain points or successes, please do submit a call, an abstract to the call for proposals. This year it's called IoT is a 4-letter word. The S stands for security. It's kind of a running joke. In any case, yeah, I'm also the Zephyr long-term support version 2 release manager. So if you have any problems there, you can probably blame me. Actually, can we take that one off the record? Don't blame me. Yeah. No, please just submit an issue and go through the regular processes, and we'll get you fixed up for the next release, the next dot release. Yeah, so just as well for the long-term support release, we've got support for 2 years, and there's a 6 months overlap. So you should be safe, and please, I encourage all of you, if you're making products based on Zephyr, use the long-term support release, and you will be good. And also, I should say, recently I was added to the TSC as a member. Yeah, so those are my community roles. Recently I did a different kind of role. Yeah, so this is me and a few other people. This was the summit spin, and I have to say this is super exciting for me. I'm really happy to be here and meeting with everyone in person and seeing everyone face to face for the first time. So I should acknowledge that this was not an officially sanctioned Zephyr event. It's sort of like a fun run where we just take part, but we don't get to see each other very often, so I figured we'd make the most of it, and I'm hoping we can do it again next year. No biggie. If you're inclined, please take part. I welcome everyone. The more the merrier. Yeah, so this is a little bit of my word cloud of Zephyr and open source stuff. So I started out in Gentoo Linux a long, long time ago. I did something with Gentoo and Bionic, which is a little bit crazy. And so we have Larry the Bionic cow down there at the bottom corner. These are some of the things I've touched on in Zephyr. I have a strong interest in Posix. I did a lot of the radio stuff for some Texas Instruments boards. Did the Graybus port along with beagleboard.org. Yeah, and I mean, like in my past life, I've done a lot of Yocto and stuff like that. So, yeah, so here we are. This is our agenda for today, route map, if you will. It's kind of like a cycling theme today. So first we're going to talk about native Posix. What is it? Why do we have it? What is it useful for? And then I'll tell you about this thing called macOS. I'm sure you've never heard of it, right? And then, of course, how we're integrating that in Zephyr and the obstacles that we've encountered. And in particular, my way of implementing things to make them work, which is in the garage, so to speak, and then finally the road ahead. So, yeah, native Posix. What is native Posix? Well, it's a bunch of things. Really, we have the arch layer at the bottom. And the reason this is capitalized is because that can refer directly to config arch Posix. and that can refer directly to config SOC Posix. And then at the top, we have Native Posix 64, and the Bluetooth simulator. Those are all the Posix platforms that I know about right now on Zephyr. And yeah, I guess technically speaking, the Arch Posix refers to running Zephyr in a user space process under a Posix host OS. Whereas we have something else called Posix API. They're not the same. So Posix API is really just a library of the Posix standard system calls, that sort of thing. Typically found under libposix, and a little bit mixed in with the C library, because that's just the nature of Posix. So currently, I'm really sad to report this, but config Posix API and config Arch Posix are mutually exclusive. I know it's very sad. It makes me sad too. Does anyone know why that's the case? It's because we have one global namespace in C. That's what we're dealing with. So when you try and link a native application with Zephyr, we're getting namespace collisions, I should say. That wasn't always the case. So actually they discovered that after they were getting linker issues in CI. To be like, hey, why are we calling, fcontrol or, all these other things that exist on Linux, but not necessarily in Zephyr. So there were some linker issues, and it turned out to be a bit more of an issue than we thought. And the Arch Posix maintainer said that we should take a step back, make these mutually exclusive until we figure out a better way. I'm not the Arch Posix maintainer by any means. I do have a strong interest in it, and I have a strong interest in the Posix API. Are we? Oh, sorry. Oh, I should have been clicking along here. My mistake. That's basically just what I said. So, okay. So, yeah. Now, if you're developing for, Arch Posix, you definitely don't want to be calling any native Posix functions that don't exist in Zephyr, because it gets a little bit uncomfortable. And so, please do not be that guy. Do not be that guy. Okay. Yeah, moving on. So yeah, why a native Posix? There are a number of reasons. The first is that we can run a lot faster. We have more resources. We can use tooling that isn't normally available to Zephyr applications, like code coverage. Faster development cycle. It's functionally accurate, remember, so we're not hardware cycle accurate. You've got more resources, as I said. You can do native debugging as if it were just a regular native application, which is really nice. Everyone loves that. You can use the address sanitizer, right? Because we love security. We love to be secure. Undefined behavior sanitizer. Everyone loves undefined behavior, right? Valgrind for memory leak detection, code coverage, and perf, because who does not love a good flame graph, right? Yeah, so there are some other reasons that were previously spoken of, but I will emphasize them here as well because I think they're fantastic. Now, as you can see in this chart, ignore the lower three areas here for a second, but that's your typical, the top two boxes are your typical Zephyr applications. We're writing applications for the Zephyr API, interacting with device driver APIs. This was already covered actually by Keith, by Simon Glass in his keynote, and by Yuval in his virtual talk. So I'm not going to go into too much detail. But the key idea with native Posix and functional testing is that you want to fail fast. You want to fail as fast as possible in your CI so that you're not wasting time before you get to testing on hardware. And of course, a large category of bugs are functional bugs. They're not bugs to do with driver code or bit stuffing inside of registers. They're to do with misconceptions about the API use. So you want to eliminate those as fast as possible. And of course, not waste time on hardware testing if you can avoid it. The other really important thing here is that your application does not change. Your application executes the exact same code paths through the operating system. and you don't have to modify it. It's a little bit of device tree changes if you want to mix it up to a different piece of hardware from your environment. But one of the really important things is that if you get inconsistencies between functional testing and hardware testing, then that's a signal. Sorry, I'm just going to get back there. If a functional test fails, then it's likely a user error, like incorrect API usage. If a system test fails, but a functional test pass, then it could be a driver error. In that case, you might want to rewrite your driver. So now the question is, why native Posix on macOS, right? Because we're, for the most part, using Linux everywhere. I see more. So, I mean, I'm a Linux guy historically. This is a Mac. I know, like, shame, shame, shame. But, you know, like, everyone has their choice. Really, what we want to do is we want to be inclusive of everyone. If we cast a bigger net, we're going to get the best developers from every community. And really, I think that benefits the Zephyr project, ultimately. Oh, lastly, I missed this point, sorry. Yeah, if we can support macOS, then we can support any Posix OS. That's my hypothesis. Just to really, I'm going to try and go through this quickly, but let's cover how native Posix works. So you register native tasks in your drivers and stuff like that. Native tasks get executed in general prior to Zephyr being started. So, and you can basically run a native task with a function pointer, execution level, which would be like prior to boot 1, prior to boot 2. And also you can run cleanup handlers like on exit, and then you give it a priority so that you can actually have fine-grained control over which tasks executes first. Then what we have is of course, just like everything else in Zephyr, we have iterable sections. We love iterable sections. So that's your system inits, your device inits, that sort of thing. Native Posix is sorted just like every other iterable section in Zephyr, so that all of the native tasks that you register get executed in the expected order. Yeah, basically once the native main starts, you end up jumping to the Zephyr app main. This is kind of a little bit of some fudging, but it's just an easy way for the Arch Posix maintainer to give you a consistent interface. So we end up including Posix Cheats, which redefines the main, and then we run through all of the registered native tasks at the beginning. We initialize the C runtime. I don't know if I'm getting ahead of myself here. Maybe I'll zoom in a bit. Yeah, so what I didn't mention is, in a little bit more detail, is Posix Cheats H. So in general, this file gets included with every compilation unit, unless you specify no Posix cheats. So you shouldn't do that generally, unless you're doing something below the line, like adding a UART driver or adding some sort of spy emulation or something like that. What the Posix cheats header does is it macros out every single Posix system call that you can possibly use, so that if you end up using it on native Posix, you'll get a linker error. And that's just really like fail fast. Don't even get to the point where you're doing something undefined at runtime. So yeah, just like every other, let's see, sorry. Okay. So when we get to the handoff between native Posix starting and Zephyr starting, we get Posix boot CPU, which calls ZC start, so it's C runtime for Zephyr, and then multi-threading is initialized. And then, of course, as I mentioned, Zephyr loves sorted iterable sections, so we run through all the sysinit, we run through driver initialization, that sort of thing. And then finally we get into Zephyr Scheduler. So that's basically arch swap, and then Posix swap, and then from there you are multi-threading, and Zephyr's scheduler is taken over. And really, it's at that point you're interfacing with arch, Posix, and that thread.c in the core part of the arch Posix. So yeah, macOS. Down the road, small town called Cupertino, company called Apple. Everyone heard of it? Oh, no? Really? They basically invented computing, right? Like, invented computers, invented the portable media player. Phones? No? Oh my gosh, okay. In that case, maybe you've heard of this gentleman who collaborated with Apple to invent gravity. Oh, okay, good. We're all on the same page. I'm very glad. Sorry, no, I'm just kidding. Apple obviously contributed a lot to computing over the years, so just a friendly joke. I mean, I like their hardware, so I'm not going to complain. Yeah, so a little bit about macOS. And I'm not going to cover this in detail. I'm no aficionado by any means. I'm relatively new to the Mac scene. So yeah, last version of the classical operating system was in 1999. It was dubbed the best operating system ever. Had cooperative multitasking. It was great. I like the user interface though. I mean, way back then it was pretty great. From 2000 to 2016, of course, we had macOS 10. And it was built on technology developed by Next, Carnegie Mellon University. It incorporated the X is not Unix kernel, which is a combination of BSD and Mach, which was from Carnegie Mellon University. And it's classified technically as a hybrid kernel, but for the purposes of this talk, I'm just going to consider it a microkernel. User space is composed of FreeBSD, Apple, utilities, NextStep, etc. And then, of course, we got Posix support on macOS 10, so that's pretty great. And X11, who doesn't like X11, right? And then, of course, 2016 to present, we've got macOS. So let's compare apples to whatever, penguins, if you will. Linux and macOS, both Posix. Linux has the GNU background, macOS has the BSD background. The kernel, as I said previously, I'm going to consider macOS microkernel for the purposes of this talk. And of course, Linux is a monolithic kernel. Executable format in Linux is ELF, which has been really great throughout the years, and we all use it in Zephyr, so it's great, right? macOS uses, I don't even know if I'm pronouncing this correctly, Macho, is that how everybody calls it? Is it Mach-O or Macho? I don't know. I'm going to say Macho because it's easier to pronounce. And then, of course, the main library. In Linux, of course, we have libc. In macOS, we have libsystem.b.dilib. And I'm going to mention something about libsystem.b.dilib, which is very unique to Apple's operating system, and that this is an umbrella library. So transparently to the user, you can't just consider this a libc, unfortunately. Transparently to the user, at link time, we have something called lc re-export dilib, which essentially means look through this hidden list of linked libraries, and then pretend that those symbols fill up your libsystem.b.dilib. Now, additionally to that, as of Big Sur, Apple did something quite interesting called the dynamic linker cache, which basically takes away all of the libraries from the file system that libsystem.b.dilib depends on. So you can't actually see them, unless you kind of do something really hacky, and maybe I'll show that to you later. I think I've linked to it. So, but in any case, system calls in Linux quite straightforward. I think it's pretty similar to a lot of other RTOSes. Where we have software interrupts, syscall number, and registers. I'm speculating a little bit, but I would say that the equivalent system calls in macOS are a function call and potentially many function calls and some message passing. So that would be the kind of microkernel categorization. And of course, we have the ELF executable linker framework, whatever it stands for. I don't even know. ELF, yeah. So we all have the binary format in Linux. It's pretty easy to understand. We've got a header. You've got your ELF64. It could contain other things like NDNS, architecture, of course. And then you've got your program header. On object files, this is 0 size because you haven't actually made a program. And then ELF is very section oriented. So you've got, the classic sections that we all know about: text, RO data, data, BSS, your symbol table, and string table. And what is a little bit different perhaps with ELF is that the section header is at the end, and it does back references into all the previous sections. In Mach-O, whatever, we've got the same kind of information in your header. You've got your NDNS, you've got your file type, that sort of thing. And then the interesting thing about Macho is that it's all command oriented. So you got load commands. For example, this first one here is actually the text load command, and it's an empty string. I don't know if you can see that clearly. The segment is actually an empty string. Sections are always paired with a segment. So that's one kind of thing we'll have to address is you've got __ text and then comma __ text. So, I mean, it's kind of an easy mapping there, but it's not always super easy. And of course, you've got kind of the same thing. You've got your text forward referencing into trailing data. So you've got your text section forward referencing data that's following all the commands. And so that's what I meant by, reverse references versus forward references. And of course, most of the section mapping is pretty obvious, but in some cases it's really not. And so this would be a little bit of fudging that would have to be done in order to kind of pawn off a Macho binary as an ELF, which is kind of the approach I'm taking. Okay, so now comes the fun part. I'm going to tell you about all the problems I encountered. Macho has a number of, macOS has a number of quirks. One is that it only supports the Macho binary format. The other thing is that it does not support weak symbols at all. You get warnings such as the one listed here. You don't get symbol aliasing. In ELF, you can do strong and weak aliases. We don't have that opportunity in Macho. And of course, as I mentioned, you require a segment name for every section name. And if you don't do that, you'll get an error as well. And of course, in Zephyr, we love to put things into different sections because that's how we get our ordered iterable structures, which are used at boot up. And then, of course, segment and section names can be at least 1 character and at most 16 characters. So this poses a problem because as you can imagine, section names can get quite long. And then, of course, we've got Zephyr. We have a few ELF hacks that we do, right? Because we have to do some compile time stuff. So, gen offset header, which is just basically telling you the size of structures and the offset of various things in the current in the binary. And then generating device handles. This is a huge script actually, and it does a lot of ELF parsing, rearranging of stuff within the ELF file. And it's actually kind of ironic because right across the hallway, Andy Ross is giving a talk about how we have a lot of issues with Zephyr and the linker, and he's talking about creating a new linker. What I found, though, is that in terms of Python, Macho tooling lags behind ELF tooling significantly. So I went ahead and I kind of did like my own thing there. Another area of sort of an obstacle is just toolchain abstractions. Our assembler doesn't support the type directive. We can't use whole archive. LD does not, Apple LD doesn't support GNU style linker scripts, which is huge. It's like a huge thing for us in Zephyr. There is something called an order file in macOS, which I'm not too familiar with. And I think that it probably does not have the ability to generate symbols, which is something that we rely on to some extent within Zephyr. Of course, Apple, everything's a dynamically linked executable or a dynamically linked library. There's no static. So yeah, this is, I guess this is the point where I say, okay, now I've listed off some of the problems, like we're good to go, we can all go home and have a beer or something, right? No. I did a little bit of work on this already. Okay. Yeah, so first prototype, bit of a dirty hack, I'm not gonna lie. I did some constructor stuff that was not very well received, and it probably wouldn't scale at all if we tried to do this in production, because there's just too many custom sections. And then, of course, I tried a suggestion, which was to use the homebrew GCC. That unfortunately didn't work because it still uses Apple's linker. Same linker problems. Then I thought a little bit out of the box. Actually, I took a loss device, so I modified Clang a little bit. I added a couple of options to Clang. So hash section names equals n, where n is the maximum length of the section name that you would like, which would be 16 in the case of Macho. And an output file, like f hashed section names equals output file. And that way you get kind of a nice forward mapping in any case. So the approach I took was SHA-256 with the section name, because it's pretty darn unique if it's SHA-256. Base 64 encoding, and then truncate to n, so that would be 16, because we want to keep as much information as possible there. I didn't come up with this scheme. I actually saw this used elsewhere. Surprisingly enough, I think it was Zig that did this, the Zig programming language. So a couple of other projects too. Yeah, I think ultimately that what we want is a drop-in replacement for GCC. So that includes linker scripts, and part of the reason is LLVM is a fast linker. So these are some of the results I've had, and it actually seems to work out pretty well. We've got the hash is generated and then a forward mapping there. That would normally be passed to the next stage along in the toolchain. Yeah, and then of course I came up with a little bit of stuff on my own. Wrote something called Macho.js, which is just kind of like a viewer for Macho files. When you hover your mouse over all the different sections, it gives you the kind of nice pretty print of what it stands for, just as a time saver. I came up with a toy linker called Lodi. It doesn't really work yet, but it's kind of getting me off the ground, so going to keep working at that. And I guess the ultimate goal would be to prototype things in Python and then backport it into LLVM. So yeah, looking forward. I think I'm going to continue to work on Lodi in my spare time. It's not something that I can commit to often, but I'm interested enough, and I hope it generates a little bit more interest from other people. We'll probably have to add some function to LLVM's linker called f-hashed section names equals input file so that we can convey that information, unless there's a better way to do that. And then, of course, I came up with something called Macho tools, which is just kind of like a PyElf tools equivalent for Macho. Still have to do section reordering, because that's quite important. And then, of course, update gen handles Py to do things like your device handles, that sort of thing. And then, of course, ultimately, we want to get that in the SDK. So luckily, I have Stefanos and I are pretty tight, so hopefully we can work on that together. The last thing I didn't really address, though, is weak symbols. And I actually had a Zephyr developer ask this question in a pull request, like, what should I do if I'm not using weak symbols? Because it's such a convenient facility for ELF. And it's like it hurts for me to say this because I know the convenience factor is really high, but use kconfig to configure software. Just like in Zephyr, we use device tree to configure hardware. That's the only solution I have right now. I think it can work, but I'm open to anything really. Yeah, so we do, if we want to get full macOS support on full native Posix support on macOS, we are going to do some QEMUing, some network tooling and stuff like that. I'd also like to get config Posix API to work with config Arch Posix. We've got some issues open for that. And surprisingly, like I'm not the only one to run into this problem with open source software and Macho binaries. So hopefully the rest of the community can benefit from the work when it's done. Yeah, I don't know if I have time for live demos, but I did prepare some in case anyone's interested. But yeah, that's basically it. And thank you. And I would love to hear some questions if you. Oh. Also, thanks for laughing at some of my jokes. That means more to me than you can imagine. Usually it's just my kids laughing because they're like, nice one, Dad, you know? Yeah, and so that's it. But if we've got any questions, a minute or two. Denny? Yes, the question was, did I take a look at the linking abstractions that are in CMake that Torsten did? Torsten's from Nordic, right? Yeah. Yeah, so we were looking at that together. He's on leave right now, and I really would have liked to kind of dig into that with him a little bit, because it's possible that maybe someone knows something about this order file, and maybe the pieces can fit together really easily for someone else. If we've got any like really, great Mac developers in the audience, I'd love to hear some advice at some point if you've got low-level details to share. But yeah, haven't dug into that too much, but I feel like the symbol generation might actually be a showstopper there, because we need things like section start, section end. They're not quite automatic, I think, with the order file. You can manually define them, but then we get into this issue with like scaling and where do we put all that stuff, and there are so many custom iterable sections. But yeah, it's a great suggestion. Any other questions?
So I'm trying to understand the use case, and from what I gather is you want to run CI on your Mac.
Yeah, I guess some like cross-functional tests would be good, but really, I mean, I just want to debug a native binary and use native tooling. I think that's like flame graphs would be pretty awesome. I don't know if we can do that yet in macOS, but other tooling, yeah, like ASAN for sure.
So this seems like a massive undertaking. Why not just run everything in one
container? Yeah, no, that's a valid point. I've just not really figured out how to debug something in a container, and I guess you'd have to have a cross tool chain for that. I mean, it's totally doable, I'm sure, but yeah, you drop a GDB server in there, and for sure. But I mean, that's just an extra step. But it's a valid suggestion for sure, though.
Yeah, I mean, this is like the holy grail. Have the tools, Docker.
Mm-hmm. I forgot I'm not sure if I repeated the question, but the question was, why not just run it in a container? But yeah, I think I agree with you. I'd rather just run a native binary, and surprisingly, the LLVM changes were not that difficult. So that gives me a bit more confidence to. And I've already been discussing with the LLVM linker developers too, and so we've come to some sort of agreement that, you wouldn't be putting this right into the Macho LLD implementation. This would.
So you wanted to use the sanitizers, right? Which are great. I mean, everybody wants to use that for testing. But that means you have to use client file, right? I guess it's kind of challenging.
You totally can. For I guess the question is, can you actually compile Zephyr with Clang? And you can, like Native Posix works for sure on Linux. It works on macOS. I mean, this is a bit dated, but yeah, it's totally doable. There is a link to if you actually want to replicate this. So pretty straightforward. Anyway, how are we doing for time?
Yeah, we should probably end here.
Okay. Thank you so much, guys, for attending.